All right, our last section, looking at solutions, kinetics, equilibrium, acids, bases, and titrations. For number 50, it says we want to calculate the molarity for these solutions. Well, we've got to remember that molarity is equal to moles divided by liters. Sometimes you're given grams, and you've got to divide by the molar mass of that substance in order to convert it into moles first. That's what we're going to have to do in question B here. The first one's pretty simple and straightforward. 0.4 moles is dissolved in 1.6 liters. Punch that into your calculator. That's 0.25 molar. The next one, a little trickier. 20.2 grams of potassium nitrate. Check charges, they cancel out, so that is the formula for potassium nitrate. I'm going to add up its molar mass from the periodic table. 1 mole of KNO3 is equal to 101.11 grams. So we've got 0.2 moles of potassium nitrate. It's dissolved in 250 milliliters of solution. So we've got to divide by 1,000 to get that into liters. And that comes out to be 0.25 liters. So I'm going to do 0.2 moles divided by 0.25 liters. That comes out to be 0.8 molar KNO3. For number 51, it asks, how would you figure out the right number of grams of solute to prepare these solutions? Well, if I take the molarity of something, which is moles per liter, and I multiply it by how many liters I need, I'm going to figure out how many moles I need, and moles times the molar mass is equal to grams. So I've got several steps here. And for this first one, I'm going to divide the milliliters by 1,000 to get it into liters. 2.5 liters times 3 moles per liter, I need 7.5 moles of KOH, potassium hydroxide, and those charges cancel out. So how many grams is that? Well, 1 mole of KOH, if I add that up from the periodic table, is 56.11 grams. So I've got 7.5 moles. So I need to multiply, and I get 420.83 grams of KOH are needed. And the way that I would make this is I would add 420 grams to the 2,500 milliliter flask. I would add some water, and I would mix it and fill to the line with water to make the solution the rest of the way, and then it would have a 3 moles per liter concentration. Letter B, I've got 2 liters that I need of a 2 moles per liter solution of nitric acid. That's 4 moles of nitric acid. How many grams is that? Well, 1 mole of nitric acid is equal to 63.02 grams. So if I multiply, I get 252.08 grams of HNO3. Same thing, to make this one, I would put 252 grams of the HNO3 in a 2-liter flask, and then I would fill to the line with water and make sure it was fully dissolved to have my 2 molar solution. For 52, I've got a concentrated solution that I want to make weaker. So that should scream dilution. M1 times V1 equals M2 times V2. So I've got a 2 molar solution. I want to know how much of it am I going to use in order to make a 0.75 molar solution and 300 milliliters of it. So I'm going to solve for V1 by dividing both sides by the 2. V1 comes out to be 112.5 milliliters. So what that means is I'm going to take 112.5 milliliters of the 2 molar solution, and I'm going to add it to a flask that's a 300 milliliter flask. And then I'm going to fill to the line the rest of the way with water, mix this up, and now it's not going to be 2 molar anymore. It's going to be weaker, 0.75 molar solution. There's another question about how much water should you add if you want to make this concentration. So this one again should scream dilution. I want to dilute a 6 molar solution, 1 liter of it, and I want to make a 0.5 molar solution. So what does my total new volume need to be in order to weaken that to a 0.5 concentration? I'm going to divide both sides by 0.5. V2 is equal to 12 liters. But I want to subtract off the original liter that was there, so I'm going to need to add 11 liters of water to that 6 molar acid in order to dilute it to a 0.5 molar concentration. Some factors that affect the rate of a chemical reaction. We talked about a lot of these in class. If you heat something up, the molecules move faster and collide more with the reactants. So the increase in temperature will increase the rate. Concentration. If you have a more concentrated solution, there's more solute dissolved in it that can collide more and again increase the rate. Surface area. If you crush something up, you increase the surface area and create more opportunities for collisions to occur. And a catalyst is a chemical that decreases the activation energy, so it makes it easier for the reaction to get going. It doesn't require as much energy to break the bonds anymore. And we learned in class that the definition of an equilibrium is when the rates of the forward and reverse reactions are equal. And we also learned about Le Chatelier's principle. If you put a stress on a system, it will react, meaning it will try to compensate. So what if you increase the number of, it says here, which of these would increase the number of moles of SO3? So how could we increase this? If we increase the pressure, since there's 2 gases on the left side, they'll start colliding more and they will produce more SO3. Decreasing pressure wouldn't do that. If you increase the heat, you'll actually increase the reverse reaction, so that wouldn't do it. And if you take away oxygen, again, it will try to shift left to compensate. So the only one that will shift the forward reaction to be the favorite is if you increase the pressure. We've talked a lot about acids and bases. They're both corrosive. They're both electrolytes, meaning they conduct electricity. But they're different in a lot of ways too. Acids have a pH less than 7. Bases have a pH greater than 7. Acids taste sour. They add hydrogen ions to solution. Bases taste bitter, and they add hydroxide ions to solution. There's other ones you could come up with as well, but those are some of the main ones. So how do you recognize an acid or a base or a neutral substance? Well, ionic bases like this one put hydroxide ions in solution. So this would break up into barium and 2 hydroxide ions. Acids often start with an H, and they will put those hydrogen ions in solution. And so letter C is also an acid, putting a hydrogen ion and a ClO3 minus. But letter D when sodium breaks apart from chlorine, I don't see any hydrogens or hydroxides, so that would just be neutral. And same with water, neutral. We learned that the pH is equal to the negative exponent of the hydrogen ion concentration. So this would be a pH of 5. Since it's less than 7, that's an acid. And the hydroxide concentration has a relationship with pOH being equal to the negative version of the exponent. And we learned that pH plus pOH equals 14. So this one would have a pOH of 2. I'm sorry, pH of 2. So also an acid. Which one has a larger hydrogen ion concentration? pH of 9, pH of 2. The lower the pH, the higher the hydrogen ion concentration. So the answer to number 60 is the one with the pH of 2. And then for number 61, it says, write out the neutralization reactions. Well, that's a big hint that they're all going to make water, because that is a neutralization reaction. But you have to figure out what the salt is that's formed by looking at what's left and crisscrossing the charges. So potassium and carbonate will form K2CO3, which means you need a couple of 2's to balance it out. Calcium and chlorine are left over in letter B, forming CaCl2, requiring a couple of 2's. And Na and SO4 are left over in letter C, forming Na2SO4, requiring a couple of 2's. Letter D is referring to letter C. What if you had 8 moles of NaOH? That's 8 moles of hydroxide ions. How many moles of H2SO4 would it take to neutralize? Well, I can look at that right away and I can say, oh, 4. Because 4 times the 2, you'll have 8 moles of hydrogen ions to neutralize, because hydrogen and hydroxide ions cancel each other out to make water. But you can also use the balanced reaction if you like that method better. For every 2 moles of NaOH, and again, I'm getting this from out front here, there's only 1 mole of H2SO4 required. So 8 times 1 divided by 2, final answer, 4 moles of H2SO4. I think my OneNote is getting bogged down with all of this writing. You're almost there. We learned that bases accept hydrogen ions while acids donate. So for this first one, this acid is going to donate a hydrogen ion from the nitric acid. And in my second example, this base is going to accept a hydrogen and become HCO3. And since H2O is the same as HOH, if that H gets ripped off, all that's left is going to be that OH. And so you can see that this is forming the basic solution with that hydroxide ion there. Then we've got some neutralization calculations. This is talking about titrations. For the first one, it says we're adding sulfuric acid to sodium hydroxide. We know it's going to make water, and we also know, we did this equation above, it's going to make Na2SO4 because of crisscrossing the charges. So we need a couple of 2's to balance this out. Then the trick is, write what you know underneath each chemical. 0.014 liters of a 0.75 molar acid. And the base this was neutralized with 0.038 liters of a question mark molarity base. So first step, molarity times liters, we needed 0.0105 moles of sulfuric acid to neutralize this base. Well, for every 1 mole of H2SO4 from the balanced equation, come back, you need 2 moles of NaOH. So we've got to multiply 0.0105 by 2. That comes out to be 0.021 moles of NaOH. And divided by how many liters of base, 0.038 liters, that's a 0.55 molar solution of NaOH. It's the same steps every time. So for number 64, it's just a different acid, HNO3, plus the base this time is calcium hydroxide. We know we make water. We know we're making whatever else is left over, which in this case is the CaNO3 in parentheses 2. So I need a couple of 2's to balance. Write what you know underneath each, dividing those milliliters by 1,000. 0.0246 liters of a question mark molarity base. Multiply your liters by your concentration in order to figure out how many moles of the acid were required to neutralize that base. For every 2 moles of the base, it's neutralizing 1 mole of the calcium hydroxide. 0.0001 moles of my calcium hydroxide divided by the 0.0246 liters of the base. This base had a concentration of 0.004 molar calcium hydroxide. And the last one, the acid this time is HCl. The base is aluminum hydroxide. We're still going to make water, and we're going to make salt. And the salts this time, the aluminum has a +3 charge. The chlorine has a -1, so this forms AlCl3. Then we need a couple of 3's out front to balance. 0.0122 liters of a 0.25 molar acid is neutralizing this 0.12 molar base. And so this question, we want to know what volume is needed. It doesn't say if it wants it in milliliters or liters, so I guess we'll get to choose. Molarity times liters. We are trying to neutralize 0.00305 moles of my hydrochloric acid. Every 3 moles of hydrochloric acid only requires 1 mole of the aluminum hydroxide to neutralize. So that's 0.001 moles of aluminum hydroxide. Moles divided by the molarity gives me liters. So 0.0083 liters. And if I want to turn it into milliliters, I can multiply by 1,000. 8.3 milliliters of aluminum hydroxide would neutralize that amount of acid of that certain concentration. So there you go. My computer